Okay, good. So, so hi to everyone. Thanks for joining. Technical issues sorted out. Yay, we're back on track and ready to go. So, for those of you who are joining, as I said before, welcome. And this is my first live actually. So, I am looking forward to us going through this paper. And please feel free to share. Um, Ask your questions as I go along if there's anything that you don't understand. And of course, I will just, if it is that we have passed the point, I'll go back to it. But just keep communicating with me so that I can know if you are following or if there's anything that I need to do to help you to better understand the concept. Sounds like we can do this? You're still hearing me? Alrighty, so we're going to know. So thank you, Ricardo. And I see I have 22 Bree. And I'm seeing Atalia Dawson and Nurse Studies. Thank you guys for joining. And we are going to go through this paper from the 2023 January. So we're going to go through and get all the answers to the questions. As I said before, please do not feel shy. You can share your answers to the questions and we will go through as quickly as we can. All right, so I'm going to now share my screen on the first aspect of the question. So let me know if you are seeing my screen. Okay, good. Thank you. So here we go. The first question says, define the period of a simple pendulum. That's what our first question says, the period of a simple pendulum. Now, what I want to highlight first and foremost as we get into the question is that when you see questions and they specify certain things, you have to ensure that you, in your response, you include those things. So, for example, the question says, define the period of a simple pendulum. It didn't just say define the term period. So, when you're answering this question, the period of a pendulum has to come within that answer. So, don't just answer to tell what the period is, what the term period means, but include simple pendulum as well. Now, I'm just going to do a little illustration to remind us what a pendulum looks like. So a pendulum is a string with a bob on it. That's in essence what it is. My drawing is looking a little bit nice. That's good. Don't worry about the drawing. So the period of the simple pendulum now will be, I'm going to just put one there and one here. And these are what we term as the extremities in terms of the motion of the pendulum. So this middle section is its rest point, and then the two on the left and the right now would be the furthest it will go in those directions. So when you are checking the period, I'm just going to number these. The period would be one complete oscillation. It's a time that it takes to make one full oscillation. So you can time it from the mid reference, which would be at this point. So it would go 1 to 2, 2 to 3, and then back to 1. So let me write that. It's 1 to 2. We could put 2 to 3, and then back to 1. So that would be the motion for a complete oscillation. Or if we timed it from one of the extremities, one of the extreme positions, we could say 2 to 1 to 3 to 1 to 2. I noticed I did a little different. I took it at each stage. So for this first one, I could have said 1 to 2 to 1 to 3 and back to 1. So if you recognize, the starting position is where it ends as well. So if it starts at 2, for it to complete an oscillation, it has to also end on 2. So that would be what a complete oscillation is. So the period of a simple pendulum is the time taken for the pendulum. Like I said, you have to include the pendulum to complete one oscillation. And you can also say to complete one cycle. So I'm going to put one oscillation or cycle. And that is the definition for the period of a simple pendulum. Clear so far? Can move on to the next question. All right. So here we go to the next one. It says table 1 shows the results of an experiment to find the relationship between the length of a string L and the period of the pendulum T. So here we have 3 columns for this table. First column is showing the length of string. Second one is the period. And then the third is showing the period squared. Now this section, no doubt they want us to fill this in. So let's read and see what we ought to do. So it says state the independent, the manipulated variable in this experiment. So if you recall what happens in a simple pendulum experiment, you would have, as I said up here it's a string with a bob attached to it. Now you would adjust the length of the string and then measure the time it takes to complete a certain amount of oscillations. So in that case, the manipulated variable would be the length, because that's the one that we change. When you're doing the experiment, you change the length. So that would be the manipulated variable. So the answer for this one is length. All right, and you'd have gotten your 1 mark there. The next question now says, complete table 1 by inserting the period squared, comma t squared, so that is the symbol of that quantity. You're going to fill that in column 3. Now, t squared simply means t times t. That's it. So t times t, that's not a t. T times t is equal to t squared. And so we are squaring these values in the column here. Those are the values we're squaring in order to get the values over here. So anybody did 0.77? Anybody square that and could share the value? So anybody have 0.77 squared? All right, not seeing anybody yet. So grab your calculators if you don't yet have them, or you can use your phone, and we're going to work through it together. So 0.77 squared is 0.59. Ah, Rashid, good job. Thank you. So I rounded to 2 decimal places, Rashid. 0.99 squared. Thanks, Nur. Got that one. Good job. So 0.99 squared now. Good job, Rashid. 0.98. 1.15 squared. $1.32, good job. Question, are you seeing the screen clearly or is it blurred? Clearly? Okay, good. All right, 1.34 squared. All right, so Rashid is on a ball. Anyone else with quick fingers? 1.34 squared. I'm going to start. It is 1 point. Okay, awesome, Rashid. So we round that to 1.80. Rashid is on fire. 1.48 squared. Yes, Rashid. Because, yeah, because we're keeping it to 2 decimal places, that's why I did 80. So 1.48 squared. Quick fingers. And Rashid again. So Rashid round it to 2.20. I'll use your 2.20. I had 2.19, but I'll round it up. And 1.62 squared. $2.62. Awesome. And then 1.17, no, 1.75. Starting off with 3 points. Awesome. Good job, Rashid. So those are the values. So we're going to mark ourselves in the meantime. Because we're doing our question and we're checking to make sure. So we got our 1 mark there and we completed the values in the table. We get our 4 marks. Excellent. So now we are going to continue the question. So it now says, using the grid provided on figure 1 on page 5, plot a graph of period squared versus length. Now we should remember, if you don't remember, let me remind you, once you get your instructions to plot your graph, you must first identify the quantities that are going on which axis. Please do not make the mistake of just looking and just say, I'm putting this one on that. No, 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 no. The first quantity that goes before the word versus or the word against goes on the y-axis. So that means period squared is y. The one that comes after the word versus or against goes on the x-axis. Please remember that that is key. So first mentioned quantity goes on the y-axis. Second mentioned quantity goes on the x-axis. So let's now go over to our graph. I did some preliminary work to kind of let it move along a little faster. I identified the scale for my graph, both axes, and I put on the quantity/unit labeling for each axis. That is key, very key. So when you are labeling your graph, you have to ensure that you put the quantity/the unit. And many times when you get your question, they will tell you what the quantity is. So if you notice here, they gave you the symbol of the quantities, the quantity. So they said period squared, they put t squared. So you just go back in your table and see, okay, t squared here, what's the unit? S squared. Same thing for length, they gave you the symbol L. So you just go back and say, what's the unit? M. And you just ensure that you label your X and Y axis properly to indicate which quantity is on which axis. So that's period squared on Y, length on X. Now, let's look at the scaling and why I would have chosen this scale. Now, on the x-axis, I'm plotting these values, 0.15, 0.25, 0.35, 0.45, and I could have gone ahead and labeled my x-axis with these values. If you did that, that would have been fine. But what I did, I chose a scale of 1 centimeter to 0.1 meters, and that is fine as well. Now remember, when you're choosing scales, the quantities that you have to plot, the largest value you need to plot on any axis should be greater than half the length of your x-axis. So if you are to plot, our largest value in this case is 0.75. So 0.75 could not be here or even here. You try to ensure that you use a scale so that the values stretch to more than half the length or more than half in that direction. So in this x direction, make sure it goes more than half. And similar thing in the y direction. So I did 2 centimeters to 0.4 seconds squared. And when I did that, my largest value is 3.06. So 3.06 will end up somewhere up here. And so you can see clearly that it is more than half the length of this y-axis. So remember to choose scales that give you that opportunity to make it greater than half. All right. So that's what we did here. So I chose, as I said, a scale of 2 centimeters to 0.1, 2 centimeters to 0.4. Another key thing I want to point out before I get into the question of plotting the graph, ensure that the spacing between your increments, I call these your increments, the spaces between the increments on either axis is equal. So don't start the first one at 1 centimeter spacing and then you continue with 2 centimeters. No, it is to be equal right throughout. So make sure that your spacing is consistent so that you are coming out with an appropriate scale and you won't lose mark for scaling. So both directions as well. Don't lose a mark because you did not ensure that your scale was consistent. Please make sure the spacing is consistent. So now we're going to go about plotting the graph based on the points we have. Now sometimes we might have to round, but as we get there, I will go through that with you. So our first point is 0.1 on the x and 0.59 on the y. 0.15, 0.15. So here I have 0.1, which means, and this is 0.2. So that means in the middle here is 0.15. Like I said, you could have labeled with 0.15, 0.25, but I chose to increase by 0.1. So quick, before we even go any further, how do we determine, let me zoom in a little bit more. How do we determine what the space, each of these smaller divisions on our graph, how do we determine the value of it? These smaller ones, how do we know by how much we're increasing? There's an easy way to figure it out. So you take the difference between your increments. So this is 0.1 minus 0, because this is the highest value, this is the lowest value. And naturally that would be equal to 0.1. And I could have done the same thing here, 0.2 minus 0.1. I'm still going to get 0.1. So this would be my increment. And then now I look at the number of spaces. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. So there are 10 spaces between increments. So what I do now to get the value of these smaller divisions, and I sometimes call them the 2 millimeter spacing. So what I do, I divide the increment by the number of spaces. So it's 0.1 divided by 10 to give us 0.01. And then after we do that, I normally just go back and check to make sure that it is accurate. So if this is 0.01, then 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09, and then another one, 0.1. So that means that increment value is correct there. And let me do the same for the y-axis. So increment is 0.4 minus 0 again. And of course, we get that to be 0.4. By the way, the increment should be the same no matter where you go. So if you go 1.2 minus 0.8, you should get 0.4. So if you realize that when you check your increment, it's different, that means your scale is not done properly. So you need to go and check your scale. So the number of spaces is 10. So again, we would do 0.4 divided by 10, which will give us 0.04. So let's check it to make sure that what we have is correct. This one might be a little bit more difficult to add, but just grab your calculators if you find it difficult. So let's go 0.04, then this one will be 0.08. Then this would be 0.12. This 0.16. This one 0.2. 0.24, 0.28, 0.32, 0.36, and then we arrive at 0.4. So if you follow this method, you will be able to determine what each of these smaller increments are increasing by, and therefore make it easier for you to find your points to plot. So let's go back. We are doing 0.15 with 0.59. And we know that this line here is our 0.15 line on the x-axis. And then we need to now find 0.59 on the y. So we have, I'm going to count from 0.4. So that's 0.44, 48, 0.52, 0.56, and this would be 0.6. So 0.59 is going to be between 0.56 and 0.6. So you have an option. You can choose to round it to 0.6, or you can put it in the space close to the 6. Now, when you're plotting points, let me zoom out to see if I'll see it. When I zoom out, more or less, I need to make it a little bigger. When you're plotting points, you either use dot, and that's, make that dot a little bigger, a dot and a circle, or an X. Those are the things you use when you're plotting points. Dot and a circle or an X. So I'm going to just delete this a little bit and go again. And I put a circle around it. The dot is not supposed to be overly big. It's supposed to be at the point, the exact center of where the point that you're plotting is, but it's not to be so large that it goes like from here and it's covering all of the space. It's not supposed to be that big. The circle can be a little bigger, but the point should not be too big. So my next point now is 0.25. Oh, I put it on 0.2. Gotta go again. So it's supposed to be here. But that's 0.525 with 0.98. So let's go here and do this one again. And that's why it's always good to make sure you check. Even though you believe you plotted it on the correct line, just go back and check. All right, good. It's 0.15. 0.25 with 0.98. So this is 0.84889296, which would make this 1. So that means 0.98, make sure it's on the right line, 0.98 would be in this space right here, right in the middle. Following along with me so far? 0.25, 0.98, okay. Next one, 0.35 with 1.32. So 0.35 falls on this line with 1.32. I hope you wrote yours on a sheet of paper so that you can follow along, so I don't have to go back and forth. So this line is 1.2242832. So this right here is 1.32. Then the next one is 1.80 with 0.45. So 0.45 would be this one. And we're going for 8. So let's check. 1.6, 1.6468, 727618. And another way you could have known this was 1.8. From here to here, we go from 1.6 to 2.0. So halfway between that, being that we're increasing by 0.4, halfway between that is increasing by 0.2. So you could have done that and say 1.6 plus 0.2 gives you 1.8. Next one, we're going to 5.5 with 2.19. So 5.5 is here. 2.19, let's zoom in here. 2.024. So that's 2.0408, 2.12, 2.16. Oh wait, no. We're using Rashid's 2.2. We rounded it. So let's put it up here. 2.2 right there. And then our next point is 0.65 with 2.62. So again, we know that 2.6 is here. This is 2.4, so this is 2.6. And this would be 2.64. So 2.62 must be in the middle here. I wonder who is plotting their graph with me. And then the last one is 0.75 with 3.06. So we have 2.8 here, 3.2 here, so we know this is 3.0. And then first one after that is 3.04, then 3.08, so 3.06 is right in here. Good, we're done plotting. Now we're going to draw our lines. So 0.75, 65, 55, 45, 35, 25, 15. All right. So I'm going to get my handy dandy ruler. Now we are going to draw a line of best fit. And please note, your line doesn't have to pass through the origin. So please do not frustrate yourself trying to get your line to pass to the origin, especially if you realize it really won't happen. Don't frustrate yourself. Now let me just put a disclaimer for this software, because I can't get like a 45.5 degrees. Sometimes it will not rotate to the angle I want it, and so it won't fit properly, but I think this one fits. So I'm going to do it as close as possible. But by hand, you will be getting it even more accurate than I can with the software. So remember, we're doing a line of best fit. And for a line of best fit, what you do, you try to let the line pass through as many points as possible. Now, for those it is not passing through, you try to balance it on either side of the line. So this one is a little bit off, but like I said, because of the limitations of this software, I am not able to get it smack where I want it to be. So you find that one is below the line here, and these two end up being above. What I would have really wanted ideally is to have one below, one above. So when you are doing your line, try to see how best you can get that. One above, one below as best as you can. All right, so that's my line of best fit. Now we need to complete our graph. We have our scale properly spaced. Increments are good. We have our X and Y labels in terms of quantity and unit. Now we need to put a title for our graph and write on our scale. And that would complete our graph to get us our full 8 marks. So we write our title in full caps at the top center. So graph showing period you can put comma t squared, and I'm going to use their same word versus length, comma L. That's my title graph showing. All right, now I'm going to put my scale, and X, the scale on the X is 2 centimeters to 0.1, and you put your unit, and that is meter. And the y-axis, 2 centimeters, I wonder if it'll go in the point, to 0.4, just about fits before the point. Okay, good. So that's 2 centimeters to 0.4 seconds squared. Once you've done all of that, we can tick off our 8 marks because we just got those 8 marks. So we are going good so far. So now we're going to the other question. The other question says, calculate the gradient S of the graph on page 5. Now, once you see a symbol given for a gradient, ensure you use that symbol. And it will be important for questions that follow. Let me say that again. Once you see a symbol given for a gradient, please use that symbol. So we see it says S. So we're going to use S. And what's our formula? Make sure you write it properly, please. It's Y subscript 2. Some persons put Y squared. No, it's not. Mathematically, if you put Y squared, that is incorrect. And it's x2 minus x1. So in other words, it's rise over run. Now, I want you to understand, because sometimes persons will put y1 minus y2. It will not change your answer as long as you are aligning x1 below y1. So wherever you put y1 in the equation, whichever side of the minus sign, ensure x1 is on that same side. Once you do that and you plug your values in properly, you will get a correct answer. But generally, we do y2 minus y1 divided by x2 minus x1. Are you following along with me? Just drop a message in the chat to say, I got it. Clear so far? All right, so now we need to find 2 points on our graph that we are going to use for a gradient. And please do not use points that were plotted. So do not just go and choose, okay, I'm going to use this point and this point. No. When you're doing your gradient, you should choose other points other than those that were given in your table to plot. So you need to go along your graph. You need to find 2 points that are not plotted and then use that as your gradient. So I'm zooming in as best I can. What I usually encourage, I encourage using points that fall at the intersection of 2 lines, horizontal and vertical lines. That way, it's easy for you to read off the coordinates. But make sure that the distance between those 2 points is greater than half the length of the gradient point, the gradient line. I'm not seeing anybody saying that it's clear. Everybody understanding? I don't see any message yet. So sometimes it can be a little difficult to find one. And guess what? If you can't find any, that falls. All right, so I'm going to use this one. And the point I use for gradient is normally different from the one I use to plot. If you can't find any that goes through the intersection of 2, unfortunately, you're going to have to use one that goes in the space, and you're going to estimate what the value is for the space. And try not to go outside of the range of plotted points. So don't choose one before the first point that was plotted or after the last one. Keep it within the range of the points that were plotted. So I'm trying to find another one now that will be suitable. All right, so I'm going to use this one. I'm going to get my ruler. And I'm going to be drawing in my horizontal and vertical lines to represent how it goes out more. So just make sure that the distance between the 2 points that you're using for gradient is more than half the length of the line. Now you can carry this point. Let me carry it all the way over. You can carry it all the way over so that you can read off what is on your X easily and your Y. All right, so you can carry it all the way across. Wait, I should have done this one first. And you draw it in broken lines. All right. So we're done with that. Now we're going to read off our points. So please note, this one is our one that we're getting x1 and y1 from, and this one is 2. So now let me write the coordinates for y1, x1. So x1, oh, this one's not so straight, but it would be on this first line. So it's 0.21. So 0.21. And the y would be 0.84. And for the second point, this is 0.67. So that's 0.67. And the y is, this would be 2.66468. 2.68. So now I go over to my formula. So S is equal to 2.68, and I'm going to put my units, 2.68 seconds squared minus 0.84 seconds squared divided by 0.67 meters minus 0.21 meters. Put a line. I'm going to work on the other side. So we do that. Anybody worked out what 2.68 minus 0.84 is? 2.68 minus 0.64. (2.68 minus 0.84). Okay, awesome, Janelle. 1.84. Nice. So S is equal to 1.84 seconds squared divided by, the next one is 0.67 minus 0.21. Okay, good. So she gave me the 0.46. Nice. Unit. So that's equal to, who has that answer? 1.84 divided by 0.86. Who has that answer? All right, so Janelle gave me something like the unit. But I'm not seeing the numerical part of it. But that unit, we need to revise that unit, Janelle. It's what's in your numerator divided by what's in your denominator. That's the unit. That's how you get your units for your graph. So 1.84 divided by 0.46, what's that answer? Nobody has their calculators out? In 5, 4, 3, 2, 1. All right. Janelle comes through. Awesome, Janelle. So yes, that answer is 4, but let's review what our unit is. So in the numerator, we have second squared divided by meter. So we can write it just like that, or we can say 4 seconds squared per meter. So either of those goes. All right. So now that's the answer for that one, 4 seconds squared per meter. And now we go to the next one. So remember, watch out for those units. I know a lot of persons will tend to say meters per second squared because that's unit that you are familiar with in working with physics. But guess what? You have to ensure that you are looking at the unit that is in numerator, unit that is in denominator, and then you write your unit just like that. So if you don't want to put it to the negative one, it doesn't matter. Just put the s squared divided by m. Cannot go wrong if you do that. So now, all right. So let's go now. So the next one says s is equal to 4 pi squared divided by g. And they want you to calculate g. Calculate the acceleration due to gravity, g. So now it simply means that we need to transpose this question, the formula rather, so that we can have g being the subject of the equation. So this one, we could do one of two things. We could just simply exchange the places, but let me just go through and show the transposition. So first we're going to multiply both sides by g. G into itself 1, G into itself 1. So we eliminate G from the right side. We now have S times G is equal to 4 pi squared. Want to isolate G, so it's being multiplied by S. So to eliminate S, we need to do the opposite operation, which is division. So S into itself 1, into itself 1, and whatever we do to one side, we must do to the other side. So therefore, G ends up being 4 pi squared over what is S in this scenario? I'm seeing S in this equation. What is S? Where is that S coming from? What does that S mean? What is that S? Excellent, Janelle. Excellent. It's the gradient. And that's why I said earlier, ensure that whatever letter they give you for the gradient, that is the letter that you use. So that when they ask you to use it in another question that follows, you are able to do it and just apply it very easily. Excellent. Rashid said gradient as well. Excellent, excellent. So that's what that S is. And so we can just substitute the value of S at this point. So we have 4 seconds squared, and I'm going to just put the division sign per meter. So that's what we have there. So we have 4 times pi squared divided by 4 seconds squared per meter. Making our life easy, we can divide or cancel out our 4. Excellent, Janelle got the answer already. So we cancel out our 4 there. What's the unit, Janelle? So G would be equal to pi squared. Now that's going to depend on what you use. If you use 3.142 squared, you're going to get a very similar answer to if you use 3.14 or if you square 22/7. And so we'll be just about very similar. So we get 9.86. And I want to know the unit. All right. The unit. All right, Janelle, I'm going to show you something. Let me get a different color ink so that I can show you this. Let me use pink. Nice color. Okay, so in essence, and I'm just going to bracket this so we know we're going over here. This would be pi squared divided by s squared divided by meter. So in this scenario, we are dividing by a fraction. And if you recall what you learned in math, when you are dividing by a fraction, what do? You multiply and you invert the fraction. So much so that would become now pi squared multiplied by, we're going to invert this. So meter comes on top, second squared goes at the bottom. Meter divided by second squared. Same math principle applies here. So let me ask now, oh, I left off the square right here. Let me ask now, what is the unit for G? Almost, Janelle, almost. You left off something. Go again. You had it in your previous answer, but you leave it off in the last one. Something is missing. You did not have that in your previous answer. Go again. Excellent. Awesome. Excellent, excellent. Meters per second squared. Excellent. And that is our answer. So as I said, you can do ms, you can do that, or you could have written it meters s to the negative 2. Well, the 2 would be negative. Oh, you have a division sign? Okay, it's good, it's good, it's good. It's good. Once you have the division sign, there's no negative. Very good, and very good, Ricardo. Awesome. So that's why you have to be careful. And that's why I always work with my units coming all the way down so that you can see what to do with them when you get to a certain point. So that's why I always advise students to work with your units. That will help you to get your answer on the correct units for your answer. So guess what? We have completed question 1. So we get our 4 marks here because guess what? Our unit is correct. If we didn't have a correct unit, we'd only get 3 out of 4. Yeah, we would. So we now can say, yay, we have gotten our 25 marks for question 1. Good job, guys. So now we are going to question 2. Question 2 needs to be zoomed. Now, I was pleasantly surprised to see this question. It seems a little easy, but do not let the easiness of it throw you off, or how you seemingly think it is easy and then you just take it slightly. No. Still maintain and read the question carefully so that you are ensuring that you are doing the correct thing. So this question, it says that you are to complete the statements by filling in the blanks with the correct word or phrase. So let's go with the first one. first aspect of this says, the formula for pressure is given by. Who has that answer for me? The formula for pressure is given by. What's the formula for pressure? Excellent, Janelle. Janelle is on a roll. Yep. Pressure is equal to force divided by area. And Ari got it too. Good. Pressure is equal to force divided by area. And Janelle went a little further and told me the definition. Force per unit area. Excellent. Very good, guys. So yes, that is our what's gonna go here. So you would write now P and make sure you put in, if it's a capital P, make it be capital. If it's supposed to be a common letter, common. Do not lose marks by using the wrong case of the letter. Make sure you put your capitals where they are supposed to be. The next part, its SI unit is. What is the SI unit of pressure? All right, so I get Newton per square meter. Good. That's one. And you see they have an R here. What's the second one? Pascals. Good. So generally, you can put pascals first. Let me do that. I prefer to put pascals first. And then put Newton per square meter as the second one. But either way you do it, they will not be marking you down. All right, so we get 3 out of 7 marks already. In fluids, pressure at all points on the same horizontal level is. In fluids, pressure at all points on the same horizontal is. Jahim Gomez, welcome. Yes, Pascal is correct. Equal, excellent. So you could put equal here. Don't worry about the fact that you see another line here. What persons also placed instead of putting equal, so let me just circle equal, that is correct. They put the and put same here, so equal or the same answers, you'll still be given the answer. So in fluids, pressure at all points on the same horizontal is equal, and pressure increases as the what increases. Pressure increases as the blank increases. Excellent, Janelle. Excellent. Increases as the depth increases. So if we have any divers, you would know exactly what we're talking about here. And we have gotten how many? 1, 2, 3, 4, 5 out of 7. Let's wrap it up for the next two. An object will float in a liquid when the dash on the object is equal to the dash of the object. First dash. An object will float in a fluid when when will an object float in a fluid? When density, not quite. Go and come again. Upthrust. Hi, Chenis. Yes, when the upthrust on the object is equal to what? And this is Archimedes' principle. When upthrust is equal to? Okay, Ricardo got it too. When the upthrust is equal to what? So when an object will float in a fluid, when the upthrust on the object is equal to the dash of the object. Wait, awesome, Ricardo and Ari. Excellent, excellent, excellent. Yes, and Janelle too. Very good job, guys. Very good job. So we just got our full 7 marks. As easy as that. We just got our 7 marks. Just got our 7 marks. So the formula is that SI unit, pressure at all points on the same horizontal is equal. Pressure increases with depth. Upthrust is equal to weight once a body is floating. Very good, very good, very good. Next question. So figure 2 shows a shipwreck which is fully submerged at the bottom of the Caribbean Sea. The liquid pressure on the top surface of the shipwreck is 430 kilopascals. Can any of my brilliant students convert 430 kilopascals to pascals? I mean, any of you could do it because you're all brilliant. So convert 430 kilopascals to pascals. What would that answer be? And while we do that, I'm reading the next part of the question. So it says, calculate the depth of the shipwreck below the surface of the sea, given that G, and we know G is going to be gravity, acceleration due to gravity, is 10 newtons per kilogram. Atmospheric pressure is 100 kilopascals. And the density of seawater is 1,025 kilograms per cubic meter. Anybody convert 430 kilopascals yet? So please note, let me get a nice color here. Let's use this orangey looking color. So this is the water. You can see that wave telling you that that's the water. And naturally, this is the ship down here. Naturally, this is our ship. So it's saying that the liquid pressure, you have to note that. Okay, very good, Janelle. 430,000 pascals. Remember, pascals is a capital P though. So put your capital P for your pascals. So surface of the water, and you have the ship here. So the pressure that it's saying is exerted on the top here due to the liquid alone. So the pressure here due to the liquid is 430. Excellent, Janelle. Yes, we use rho GH for density. Regular formula, right? So this is pressure is equal, fluid pressure is equal to rho GH. Rho for density, G for gravity, H for depth. Very good. So you have that shipwreck. The pressure here due to the liquid alone. So let me put P and put an F down there so you know that's fluid pressure is equal to 430. And I'm going to just put my kilo to be 1,000 kilopascals. That's on the surface there. Now up top, on top of the surface of the water, what kind of pressure is the surface of the water exposed to? Hi, Matthew. Thanks for joining. What is the surface of the water here? I changed the color. What is the surface of the water? What kind of pressure is it exposed to, experiencing? What kind of pressure? So let me put my P. What kind of pressure is it up there? All right, let's do a fill in the blanks. Start with A. starts with A. It has 10 letters if I'm spelling properly. Or you could say it has 11, depending on depending on how you are going to say it. Excellent, Ari. Atmospheric pressure. Excellent. Atmospheric pressure. That's the one. So up surface here, it is atmosphere, and I'm going to put P and subscript ATM. That's what's going on at the surface of the water up there. But the ship down here, based on the fluid alone, it is 430,000 pascals. So let's go back to my black ink. Now the question says, calculate the depth of the shipwreck below the surface of the sea, given that G is this, atmospheric pressure is that, and the density of seawater is that. So, sometimes they tend to give you some information that is not necessarily relevant in an effort to test if you really know what you know. Right? So in this question, they did that. But do not fear. Just as, who was it earlier? Janelle, who asked about the formula. You know the formula. So you just apply the formula and the quantities that fit for that. So it's asking you for depth. You know that pressure is equal to rho G H, where P is pressure. This lean looking P thingy is called rho, which is a symbol for density. G is a symbol for gravity, and H is a symbol for depth. So you know that. So do not let this, and I'm going to put it in red. Do not let this throw you off. And how would you know that that wouldn't factor in the equation? Because they're asking you to find depth. Now, the formula that has depth is fluid pressure. Let me put my subscript F. Fluid pressure, and that is it. So don't be thinking you need to find total pressure. Don't be thinking that. They told you the pressure that is on the top of the ship. So that means you can apply the formula rho GH and just transpose to make H subject, and then you move from there. So let's go transposing. So we want H to be by itself. It's currently being multiplied by rho and G. So we do opposite operation. So we divide, and whatever we do to one side, we must do to the other. So that's going to cancel, that's going to cancel. So they said depth, making sure that we're doing the right thing. So H is equal to fluid pressure divided by rho times G. So that now becomes, fluid pressure was the 430,000 pascals divided by, they told you what density is. Density of seawater is 1,025 kilograms per cubic meter times 10 Newton per kilogram. Like I said, I love to write out my units. So if you can follow along with me, I'm just going to cancel out the units as they are. So kilogram going to cancel the per kilogram. We know that pascals is Newton per square meter. So I could have gone through and show you the complicated, but I'm not going to do that. Just have you know that they would cancel. So somebody now tell me, what is 400,000 divided by 1,025 times 10, or 10,250? Or I could have taken off a 0 from numerator and denominator and said 43,000 divided by 1,025. Anybody got my answer yet? Excellent, Rashid. Jahim, you missed out your decimal point. What is the P? The unit though, Rashid. The unit though needs a little review. We're asked to find depth, and what would be the unit of depth? Depth is a distance. So check the unit. Excellent, Rashid, meters. So if you want, do you want me to do a side just to show you why the unit ends up being meters by eliminating units? Want me to do that? Or you are fine, you understand why we have meters? Yes, you understand, or yes, you want me to show you why it's meters? Okay, I can show it. All right. So here we go. Instead of using Pascal here, let me highlight. Instead of using Pascal here, I'm going to use the other unit for pressure. So it would be, use a different ink so you can know that I'm showing you something. So it would be 4,000 and 430,000 Newton divided by meter square divided by 1,025 kilograms per, let me put the division, meter times 10 newtons divided by kilogram. All right. So we can see this kilogram is denominator, so it can cancel this one that is a numerator. Then this newtons is going to cancel this newton. So now we will have meter squared divided by meter cubed. So let me do that to the side. So notice we've eliminated all other units. So meter squared, if we write it in expanded form, it's m times m. And meter cubed is m times m times m. So these two will cancel. So that your answer will now be, and notice this is in denominator. So your answer will now be, what was it? 41.95 and divided by, now remember the meter cubed was a denominator. So divided by 1 divided by meter, only 1 meter is left because we cancelled. So that now becomes 41.95. When you're dividing by a fraction, you change it to multiplication and invert. So that gives you 41.95 meters. All right. So Janelle asking if I'm going through the entire paper tonight. Tell me what you want. Would you want me to go through the entire paper tonight? Or you want me to pause? We're at question 2, not quite at the end of question 2 yet. It's now 8:30. Tell me what you would prefer. I can go through the entire paper though. All right, Ari, I'm seeing you say you got that. Awesome. So do you want me to go through the entire paper tonight, or you want me to continue another evening? All right, we could continue tomorrow if it gets too late. Okay. All right, so I'm just getting the other questions. Going up to at least question 3 tonight. Okay, so the next question that we're going to, hold on, let me get this last one. Da-da-da. Next question we're going to says, calculate the total pressure on the top surface of the ship. So again, don't be confused, just know your formulas and apply them. Total pressure is equal to atmospheric pressure plus fluid pressure. So let's go. I'm going to put total here is equal to fluid pressure plus atmospheric pressure. So if you recall, the fluid pressure was given, it's 430,000 pascals, and the atmospheric pressure was given 100 kilopascals. And that's a value that you should know as well. One of those constants that you should know. So by quick calculation, that ends up being 530,000 pascals, or you could say 530 kilopascals. And that would be your 1 mark. Didn't record our marks for this one. That question was worth 4 marks. So we got our 4 marks for this one. So now the final question in this one says a hatch door on the top surface of the shipwreck has an area of 0.60 square meters squared. Calculate the downward force on the hatch door due to the total pressure on the surface of the shipwreck. So let me just underline the key things. They want you to calculate the downward force. And it's due to the total pressure that is there. So no trick again. So what is the formula for total pressure again? Not total pressure in this case, because they want you to find the force. So you know that if you are to find total pressure with atmospheric plus fluid, you don't see force in that equation. So you would say, all right, let's back up a little bit. Jaim asked, let's put this question, where the 100,000 came from. Okay, so let's go back to that part. The atmospheric pressure is 100 kilopascals. So if you do, and thanks Janelle for assisting him. So when you have 100 kilo stands for 1,000. So you would have 100 times 1,000 pascals. So that's how you ended up getting 100,000 pascals. And that's the same thing we did with the 430. Right, we got 430,000 pascals. Clear to you, Jaime? Awesome. So the formula for pressure, like we established before, the one that has the force in it is force divided by area. So they asked us to calculate the downward force, so we want this as our subject. So again, transpose, it's being divided by A. So you multiply both sides by A. So you cancel, so that we can say therefore force is equal to the total pressure times the area. And that would be total pressure. We just calculated it in this previous question. Janelle, you missed the letters. You have P equals F times A, interchange F and P. So this would be 530. It happens. 530 pascals times the area that they gave us, which is 0.60 square meters. Who has that calculation? I can tell it starts at 3. Janelle, you need some extra lesson. Which grade are you in, Janelle? You've been doing well so far, though. You've been doing extremely well. Excellent. And as I speak, you're the one who gives me the answer. You've been doing extremely well. And what is, you're in grade 11, you're doing well so far, don't worry. What's the unit of force? We're asked to calculate force. What's the unit? Remember, when you're giving your answers, you have to have a unit. Let me tell you how your paper is going to be marked. Good, Janelle. Tell you how your paper is going to be marked. Make give you just a little awesome, Janelle. Tell you that you're doing well so far, you know. So, let me get my reading. 3 marks is broken down, 1 for your formula, which is why us as physics teachers keep preaching, write your formula. So you get 1 for your formula. Let's put it here, because you gave the correct formula for force, which is what they ask you to find. You get 1 mark. You substitute the correct values for what the letters represent, you get an X mark. You put the correct answer on the unit, you get 1 mark. Now, naturally, if you have the correct answer, so if you only place 318,000, the most you would have gotten is 2 out of 3. Units are very important. So make sure you always write your units. You can't have a measurement without units. All right, so that's that. Now we get to this lovely question. This one, it's about thermal energy. So figure 3 shows a section of a white plastic pipe through which water is flowing. So, you know, like your pipe that leads into your home, that kind of a setup. So it's showing that the water in the pipe is heated by the sun. So, you know, I don't know where you guys are from, but if you are from the cooler parishes in Jamaica, you would appreciate taking a shower close to midday, because at that point the pipes get a little heated. What was the answer? The answer was 318,000 newtons. Got that? So yes, so you would appreciate taking a shower closer to midday, because especially if your pipes are exposed, meaning they're open to the sun, at that time of the day the water warm. So you're not going to struggle to take a shower. Right? So you'd appreciate that. So that's the kind of setup that we have here. Right? So we have the white pipe, and naturally the color that they tell you, you have to make sure that you pick up all of these little information they're giving you. They tell you that the pipe is white. They tell you that it is plastic. Those are important. And they tell you that it's being heated by the sun. Important information. So let's go to the question now and see where it applies. Describe how thermal energy is transferred from the sun to the water inside the pipe. All right, so Janelle is along the path, getting there. So they're asking you to describe, and we know thermal energy means heat energy. We know that. From sun to the water inside the pipe. That's what they wanted to do. And note they said describe. So describe means you're going to write. You're going to tell them about what is happening. So heat from sun to the pipe, and I'm going to write it in point form. You can write it in full sentence form. Good. So you're using the correct terms, Janelle. So the heat from the sun will warm the pipe by radiation. Remember, I'm putting it in point form. You are putting it in a full sentence. So heat from, oh wow, I forgot the sun. Heat from sun warms pipe by radiation. All right. The pipe then heats the water By what method? Since the pipe is a good insulator, the heat insulates the pipe. Oh, right. It is a good insulator, true, but it is going to be heated by the sun through radiation. Then now with that pipe being heated, it's going to pass on the heat because the water will be in contact with the inner surface of the pipe. So though it is an insulator, this will happen. It will still get heated. It just means that it's not transferring heat as quickly as a metal, but it will still get heated. So it's heating up the water by, remember radiation is traveling through a vacuum. So it's heating the water by a C word, C-O-N word. Which of the cons? Excellent. Conduction. Hi, Casey. Heating the pipe by conduction. The D1. The D1 channel. So the pipe then heats the water by conduction. Now the water in turn, within the pipe, we are assuming that the water is flowing. So the water itself will become heated by a mix of conduction and convection. So conduction because you are having the mass water moving from point A to point B. So as it is heated, it's moving to point B. And minimal convection because you won't have much convection currents building up, having time to build up. So whether you put convection, conduction, you would still be credited at the points. So then, the pipe then heats the water by conduction. You could have left it there, or you could have said the water at the point where it is heated, then transfer the heat to the other water. So you can say the water at the top or the water at the exposed surface becomes heated and transfer that heat to the water that is not in direct contact with the pipe. So it's 2 marks. You could have stopped it there. So you could have said heat from the sun warms the pipe by radiation. Pipe then heats the water by conduction. You could have left it there. Or as I said, you could continue. The water at the surface then transfers the heat to other other molecules by conduction and convection. That does not look like convection. That's convection, okay, guys? So the convection, like I said, will be minimal, especially if it's a case where the water is flowing right through. But if the water is held in the pipe at any point, then you will have convection currents building up and so causing the water to be heated by convection. So we're just covering our bases. Next one says now, suggest 2 ways in which the efficiency of the thermal energy absorbed by the water in the pipe may be increased. So it says 2 ways in which the efficiency of the water absorbed by the water in the pipe may be increased. So generally saying 1, put pipe in direct contact with sun. Remember, that would be a good answer. But remember, it says in which the efficiency of the energy, the heat absorbed. So it's already the water the question is taking it from the point where the water already absorbed the heat. How can you increase that? So it says again, suggest two ways in which the efficiency of the thermal energy absorbed by the water in the pipe may be increased. So basically, you don't want it to lose it too quickly, or maybe we could look at it to say you probably want it to take heat in rather more quickly. So when you say put it in direct contact with the sun, you're kind of on a roll, but it's already in the sun. So you have to word that a little bit. All right, so Ari is on a roll too. If it was a metal and dark color, that's along the line that we're thinking. So you can, one, to increase the rate at which the water is heated, you can make a metal pipe. Use a metal pipe that, as you were talking about earlier, Janelle, with the plastic being an insulator. So if you use a metal pipe, which is a conductor, the water going to heat up faster. Then now, we also know that if something is a good absorber of heat, what is it also? If something is a good absorber of heat, what is it also? So we can say one, use a metal pipe instead of plastic. I'm putting your answers together. We have this, there's this saying, good absorbers are good all right, starts with E. Hopefully I'm spelling it right. Very good. Emitters. EMITTERS. Good absorbers are good emitters. So that's one way we can use a metal pipe instead of plastic to increase the rate at which the water is heated. Awesome. But if we use a metal pipe, it's going to increase the rate at which the water is heated, yes, but we just said that good absorbers are good emitters. So that would simply mean that the pipe would lose heat equally fast. So whereas, as Janelle mentioned earlier, plastic is a good insulator. So when it receives the heat, it won't pass it on so freely. So it's going to hold it a little more than a metal. But even though that's the case, we have our metal pipe. What can we do to limit the rate at which the heat will escape? So we're increasing how quickly it's heated. But remember, that will also increase how quickly it loses heat. So what can we do to prevent it from losing heat quickly? Going once, going twice. Sold. Okay, let me tell you, one way you can solve your problem is to get insulated material to limit, we could say get insulated material to limit heat loss. If possible, we could also say use pipe, as I said, if possible, with silvered inner surface. And I'm putting an asterisk for this because that's if possible. What does the silvered inner surface do? And 4, right, it keeps heat inside because the silvered surface will reflect the heat. Very good, Janelle. Very good, Casey. So our 4, we could use a larger pipe. Use a larger pipe so that more surface is exposed to the sun. So I gave you 4 options. You can pick, choose, and refuse. All right, no, this is not the final part. Let me get the last part for question 3. All right, so here we go for this question. Rachel, don't know if we have any Rachel in here. Don't know if we have any Rachel, but Rachel used a metal spoon to stir hot liquid in a cup as shown in figure 4. It sounds like she's having some tea. After a short time, Rachel observed that the metal spoon felt hot. They always have these heat questions. Oh, yes. Describe the 2 ways in which thermal energy is conducted through the metal spoon at the molecular level. And again, you have to be careful when you're answering these questions. Make sure you don't just explain 2 ways in which heat can be conducted. It was specific to say at the molecular level. So you got to give them what they ask for. So, first and foremost, we know that once you have a metal, such as a spoon, in this hot liquid, we know for a certain, because we live this experience every day. If you're drinking tea, you leave a spoon in the tea too long, by the time you take out the spoon or you touch the spoon again, you're going to feel the heat. You leave the spoon in the pot, while the pot is being heated, the spoon going to get hot. Even if you have turned off the stove, but there's still heat in the pot that it can transfer, gonna get hot. We know this already. So now we're applying that knowledge to this question. 2 ways in which thermal energy can be conducted through the metal spoon at the molecular level. So we need to talk about molecules and how they move. So the metal spoon, as it stated, is a metal, which means that it has free electrons. In the atoms of the spoon have free electrons in those outer shells. Right? Those free electrons going to get heated first. And just like Janelle said, Janelle, I tell you that you're doing well, I tell you you're doing very well. Just as Janelle said, they move fast when heat is applied. Good. So that's what Janelle is saying right there. And then Casey are helping her out, adding to the conversation. I like it. And she's saying kinetic energy. Excellent. So we are talking about the molecular. All right, so Janelle here again. Solid particles are closely packed. Heat reaches fast to the spoon through conduction. Excellent, Janelle. I tell you that you're doing well. You're doing well. I have faith in you. So, very good. So, we're talking about first those free electrons. So, those free electrons now. So, two ways. Number one, free electrons. And if you do chemistry, you might tell me valence electrons. So, those free electrons will be heated, causing an increase in their kinetic energy and also the number of collisions. As they collide with other electrons, heat is transferred. And the second one that we're going to look at now is just as Janelle would have stated, as you have solids, the molecules are tightly packed together. And so as the molecules close to the surface become heated, they start to vibrate a little faster. And because they're so tightly packed, that vibration is spread to neighboring molecules, and therefore that ends up causing, you would say, a ripple effect. So it ends up causing other particles to vibrate, and that vibration continues as a chain reaction, basically, so that the heat now becomes throughout. It travels throughout the spoon. So where were we? We're talking about now. So the molecules. So let's say solids. As I said, I'm incorporating what you guys are saying. So solids are solid molecules. Let's say that. Control Z. Good. Solid molecules are closely packed and so as those at the surface become heated, and we know the surface of the spoon or the part that is in contact with the spoon. So those, let me say it that way, those in contact with this the liquid so those in contact with the liquid get heated and increase kinetic energy, thereby causing, that's not thereby, neighboring, that's a U, and that's a B, molecules to start vibrating. This chain reaction continues until the spoon is heated. There we go. Hopefully you can read that lovely handwriting that I just did there. Hopefully. All right. So the next question now says, the metal spoon was replaced by a wooden one. Rachel observed that the wooden spoon did not feel hot. Hi, Tafari. Explain why the wooden spoon did not feel hot. Who wants to take that one? Why did the wooden spoon not feel hot? Which is why sometimes we opt to use metal wooden spoons instead of metal spoons, or plastic spoons instead of wooden spoons. Why is the wooden spoon not feeling hot? Okay, good job, Janelle. So the wood is not as accessible to heat as the metal. The wooden spoon is a poor conductor of heat, hence it is a good insulating material. Excellent. Poor conductor. Very good, Janelle. Very good. So let me just add these. So you said that one. Wood is not as accessible to heat as the metal. And then the wooden spoon is a poor conductor of heat, hence it is a good insulating material. And Janelle again says poor conductor. Excellent. Very good. So you are all very much correct. Miss, when you're finished, can I take a screenshot of the top? Sure you can. So wood is a poor conductor of heat. And guess what? You see those free electrons that we spoke of in the metal up here? Wood does not have that, because for wood, the molecules in the outer shell are tightly held together. So you're not going to have that situation where those free electrons or free molecules are receiving heat and therefore moving, increasing their kinetic energy so much that they're increasing their collisions. You're not going to have that. So what will happen is that they are tightly wound, so it's going to take those that are in contact with the liquid, those will be heated, they will start vibrating, yes. However, the chain reaction will not happen as quickly as it does in a metal, because those free electrons, free molecules that are there moving around, they are not only going to be moving to the molecules that are at the end there. They can go in between and transfer heat much more quickly than even neighbor to neighbor. So that is the reason. So wood is a poor conductor of heat. Therefore, the molecules that are in contact with the liquid do not pass on, or let's use the correct term, transfer, do not transfer thermal energy as easily as metals, and so only, or should I say mainly, that portion will be heated. So that's why if you use a wooden spoon, what you find, was that Ari? Ari, you can take the screenshot now. So that's why when you use a wooden spoon, yes, the part that is in contact will be heated, but the heat isn't going to transfer as quickly. No, I do not do chemistry, Janelle. I don't. I know enough chemistry to help myself, but not enough to teach it. I am a physics person. Physics, TD, and BMed. Those are my subjects. Okay, and Jahi was asking what other topics will be coming. Okay, so question 3 is heat. Question 4 is electromagnetic waves, has refraction in it. Question 5 is electric field. Question 6. So we have electric field. We need to calculate. What are you calculating here? Charge, calculating resistance. And then question 6 is radioactivity, where you're filling out a table, defining isotope, and then completing an equation to show the decay of polonium into lead, and then half-life. And then that wraps up for the rest of the questions. So we're at question 3 now. Honestly, I'm inclined to take the suggestion that we pause. So I'm going to pause at question 3, and then we pick up 4 to 6 in another session. So we're on to the thermometer. So this now is taking us into specific heat capacity. So a thermometer is placed in a plastic cup containing 20 grams of water and gives a reading 22 degrees Celsius. So water 20 grams, it has a temperature 22 degrees Celsius. Small pieces of ice at 0 degrees Celsius are added to the water one by one. The mixture is stirred after each addition until the ice melts. 200 grams, right? Oh, you're preempting my question. Hi, Shelly. How are you? Thanks for joining. So Shelly is a fellow colleague, and she does IT. I know you guys have done IT already, but just in case you want or you haven't done it and you're thinking of, you can go and check her channel. So just Shelly put the link to your channel so that they can go over, check out the videos. Oh, you're checking in with me. Thank you. Janelle says she knows you. Awesome. All righty. So we have the question now. Oh, I'm not finished reading the question. Small pieces of ice at 0 degrees Celsius are added to the water one by one. So consider you want to get a drink of water. That's the scenario, basically. The mixture is stirred after each addition until the ice melts. The process was repeated until the temperature recorded by the thermometer was 0 degrees Celsius. The total mass of ice added to the water was 60 grams. First question. Calculate the thermal energy lost by the original, underline original volume of water in the beaker. Given that the specific heat capacity of water is 4.2 joules per gram per degree Celsius. There you go. Oh, Janelle just added it. Awesome, Janelle. So there you go, learning IT with Shelly. Good job. So you can go over there if you're not in grade 11 as yet and haven't done. But even if you get to sixth form, she does computer science as well. So that's a good link. So we have the question where to calculate thermal energy lost by the original volume of water in the beaker. And I saw the formulas coming through already. I saw the mass. Casey and Janelle gave me the mass. And Rashid gave me the principal heat loss equal heat gain. Very good. So now let's look at what this question requires of us. We can use the correct formula. So thermal energy lost by original volume of water in the beaker. Let me ask. They're asking about the original volume. Would you say that they want you to include the ice in this? Would you say they want you to do that? Do they want you to include the ice? While I wait, Janelle says probably. While I wait, I'm just going to, a picture says 1,000 words. So we're going to put it together. So they gave you specific heat capacity and they want thermal energy. What are the formulas that you know for this section of the syllabus that deals with thermal energy, heat energy? What are the formulas? Lay them down and we'll put them and see which one applies. So we have water here. And the water is 200 grams. Janelle, I'm assuming that is typo. Oh, no, it's not. No, it is not. I just figured it out. Yes, Janelle. Got you. So Janelle said MC triangle T. Good. I just saw that. Good job. Or anybody else who may say, we could also use MC delta theta. You use T when you're dealing with Kelvin temperature and theta when you're dealing with degrees Celsius. See, C equal MC, but we don't have any heat in that one, man. There's no heat energy in that one. That one is showing the relation between heat capacity and specific heat capacity. Yes, there you go, Janelle. There you go. You got it. All right. So we have water here. And it says we are looking at that original. But the water converted to water. This temperature was what? 22 degrees Celsius. And it went to water at what temperature? That water don't look like it's spelled water. Let me fix that. So we're moving from, so the water at 22 degrees Celsius, what was the temperature of it after the ice was added? But we're still only considering that volume. And the volume would be the 200 grams, same mass. What was the temperature of it after the ice was melted? Zero. Good job, Janelle. So naturally, this equation is our equation of choice. We wouldn't use the method of mixtures where we're saying heat energy loss equal heat energy gain and then include the ice, but the concept is applicable. But we wouldn't use it in this question. There's another question that's coming that we need to apply it for that one. So we will do EH, heat energy, equals MC, and I'm going to use theta because we're doing degrees Celsius. You may also see instead of EH, you see Q. Same thing. Q is a symbol that is also used to represent heat energy. All right. So there we go now. And I'm going to substitute because they want the thermal energy. So I have the correct subject. So the mass was 200 grams. And I can use 200 grams because the specific heat they gave me, see the grams right here. So I can use it. If they gave me it in joules per kilogram, then I would convert my mass to kilograms. But they gave me it in grams rather, so we can use it. Specific heat capacity was 4.2 times 10. No, there's no times 10. Force of habit. Because I normally work with the kilogram one. Okay, and this is joules per gram. You put the division. And degrees Celsius. So gram times degrees Celsius are in the denominator times the temperature change. So let's work out delta theta over here. Delta theta would be equal to 22 degrees Celsius minus 0 degrees Celsius. If you wanted to stick to say, okay, final temperature minus initial, you would have 0 minus 22 and get negative 22. That can also be applicable because your answer would then be in negative and you would say, okay, that is the energy that was lost. You can, not a must, because they didn't ask you for that specific. So they just ask you for the heat energy that was lost, so you can give them in a positive answer. If they asked you just generally for the heat energy, they didn't say whether it was gained or lost, then now when you calculate and you get a negative, you can say this energy was lost. So, okay, good case here, seeing that one. Who has the answer for this one? I'll cancel unit in the meantime. So joule going to cancel this joule in denominator. This numerator cancel this denominator. What's the answer? 200 times 4.2 times 22. 18,480. Excellent, Janelle. What's my unit? Can't leave off our unit. Excellent. 18,480 joules. Excellent. And is this the final? This is the final one. Assume that all the thermal energy lost by the original volume of water, which is what we just calculated, is transferred to the ice. Calculate the specific latent heat of fusion of ice. This is where now that equation or that principle, heat loss equal heat gain. And we just state that at the beginning of our work. Heat energy lost by water equals heat energy gained by ice. That's what they want us to use to do this. So, okay. Oh my, I was about to ask the question. I was about to ask for the formula for latent heat, but you guys got it. You got it. That's good. And so, if you remember, once you have a change in temperature, which we would have done up here, once we're dealing with a change in temperature, we know that we are staying in the same state. But once we're dealing with latent heat, then there is a change of phase or a change of state of matter. So this time it is going from ice to water. That's what happened. So let us go and calculate. So I got my formula already because my people are just firing tonight. EH equals ML subscript F. Good job. Did I just say F? F. So they want us to find what? They said the specific latent heat of fusion of ice. So that means LF. That's what we're making as our subject. So it's being multiplied by M. We divide. And whatever we do to one side, do to the other. So M cancel M there. So latent heat of fusion is equal to heat energy divided by mass. And that becomes the heat energy. They said, imagine that all of it that was lost is gained. So the heat energy is 1840 joules. And the mass of ice, let's go back to the top. Good job, Casey. The mass of ice is given here, 60 grams. So dividing by 60 grams. Who has my answer? Casey. I'm not seeing a unit though. So you're not getting the mark for the answer, though the numerical part is correct. So that is the answer, but it is not complete. That's a numerical part. But it's not complete. What's the answer? Excellent, Janelle. Told you were getting it. Awesome. So, Joule, you can put a division sign per gram. Good job. And that's your answer. So, we just got, can we get our 1 for our formula, 1 for substitution, 1 for answer and unit. We get our 3. Excellent. And up here, it was 3 marks, 1 for formula, 1 for substitution, 1 for answer and unit. 3 marks. Good job. Oh, we didn't do over here. We got our 3 marks over here without a shadow of a doubt, and our 2 marks here. So we have gone through 3 papers. Oh, we got more than 2 here because I gave you 4. We got our 2 here. So that is a wrap. So we have gone through questions 1, 2, and 3. See if I can give you guys a round of applause. See if I can find that one. Why they don't have that? But let me send cheers. Very good, guys, and hearts. And the 100. Yeah, you guys win. So good job, everybody. We completed questions 1 to 3, and you did very well. Even the persons who were feeling like they can't manage or they don't feel like they were at the level, I hope you are even a little toops more confident in your abilities, and you will go into more preparation feeling that actually not as bad as I thought I was. So I got this. Right. So for tomorrow, though, we're going to go a little bit earlier than 7 because, it's to 10 and some of us are normally asleep at this hour. So I will schedule it and tell you what time tomorrow. I hope none of you have an exam tomorrow. Or if you do and you miss the live, I hope you don't miss the live because I like the interaction. But I hope. How are you going to know how to interpret the questions? Right. Very good point, Casey. Draw diagrams. And when you draw your diagrams, you also write the formula. Which formula is applicable here? And what are the quantities that I need to plug into this formula? That's the kind of reasoning you're doing with yourself in the exam. And that will help you. So don't just look at all the things that they give you in the question and think, oh my God, I need to use all of them. No. So just look at what is required, what they ask you for, write down your formula, and then substitute your values. Jahim is asking me which other days will I have classes. So I want to do a live tomorrow and another one Saturday night. I'm giving you Sunday to rest. Not going to push you on Sunday. So I want to have another one tomorrow and another one Saturday night. And then thereafter you go and you prepare yourself for your exam, please. I always encourage my students to make sure they get sleep. I always share my experience. I was studying for an exam and I stayed up quite a bit. And unfortunately, when I got into the exam, I fell asleep. I slept a good half hour. So I always encourage my students, day before your exam, night before your exam, make sure you get some sleep. All right, so time for tomorrow. Tomorrow, as I said, is going to be a little early. Gonna leave that time. So tomorrow might be 4 to 6. I'm thinking 4 to 6 tomorrow. And then on Saturday, that will be night again. So that one might be 7 again. And then another question from Casey. What do you think is the maximum to score on paper 2 to pass? Maximum. All right, so maximum is to get everything. Minimum, though, I'd say the minimum for you, bearing in mind that your SBAs are having a weight as well. There are 6 questions. The paper is marked. Let me check again. So 15 times 5 is 75 plus 25. The paper is marked out of 100. So I'd say try to get at least 75 out of the 100. Anywhere you're clocking from 80s up, you are definitely in the rank to get a 1. But try to budget yourself. Put your target at no less than 75 out of the 100. Once you do that, you are in a good place to get a 1. So make sure you answer as many questions. Try not to leave blank spaces as much as you can. Try not to. So let's go through and try. All right, and leave no question blank. Not to mention multiple choice, even though we're not there yet. Never leave a multiple choice unanswered. It's better you guess it. 50% chance you will get it right. So with that, I say thanks again for joining. And I do hope that you gain a lot from the session tonight. And looking forward to seeing you again tomorrow and Saturday. No, Jahim. Jahim is asking if they're the ones coming. Okay. So previously, due to COVID, they did give the topics that are coming. That, however, is not something that CXC normally does. The reason they did that is because of the challenges that students would have had in preparation. So what we did today, I did the paper from January 2023, working through it so that you can get practice in solving questions. So we don't know what topics are coming this year. So you just have to make sure that you are as prepared as you can be. All right? And Janelle said she did. Awesome. That means she did gain a little bit more confidence in herself. Awesome. And then we close off with Ari saying, you got this, guys. Thank you for joining. See you next time. You're welcome, Jahim. And my little thing that I normally do when I do live for my church. This live stream will end in 5, 4, 3, 2, 1. Bye.